Okay, everyone, we're going to get started with today's webinar because it is a detailed webinar that our practice lead in structural, Andre Cullen, is going to take us through, and there's a ton of information today, so we'll get going. I will just share a couple of housekeeping notes. At the end, we will be having a Q&A, so if you have questions, you can type them in the chat and we'll address them at the end of the presentation. Throughout the presentation, we will be having a couple of poll questions. We do ask if you can participate and answer those questions. And then at the end of the presentation, of course, before you leave, if you could take some time to do the survey, that's at the end of the webinar. It allows us to bring appropriate topics to you based on what you want to hear from us. So at this point in time, we'll get started, and I'm going to turn it over to Andre Cullen, who's going to talk to us about the challenges of extending the life of your historic structures. Andre, it's over to you. Your mute is on, Andre. There you go.
Thank you. Thanks, Amanda. So just wanted to do an introduction. My name is Andre Cullen. I'm the practice lead for Roth IAMS. I've got 25 plus years of experience in design analysis and forensics. I studied at the University of Alberta and specializing in all the materials, steel, concrete, wood, and masonry. And we are for Roth IAMS, we have a team of about 7 structural engineers across North America, US, and Canada. And as you can see by the background, I am in Alberta and the Rocky Mountains. So I'm just close by there, about 3 hours away from the Rocky Mountains, but in Alberta. So for our topic today, we'll be talking about historic structures. So on the agenda, we have an overview at first of why our historic structures matter. Then we'll be looking at conservation, what is conservation? And then we'll be talking about uniqueness, structures, materials, and design features, and touching on challenges in operations and maintenance, and then planning for the future. As well, we'll end off with just a little bit on specialized preservation and some questions to follow. So why are historic structures matter? What are historic structures? Historic buildings are physical structures that give us a sense of wonder and make us want to know more about the people and culture that produce it. They have architectural, aesthetic, historic, documentary, archaeological, economic, social, and political, as well as spiritual and symbolic values. But the biggest impact is always emotional, and that's a symbol of our cultural identity and continuity, a part of our heritage. So if it has survived the hazards of 100 years of usefulness, it has a good claim of being historic. So first acts of creation through to this long life of present day historic building has artistic and human messages, which will be revealed by the study of its history. Complex ideas and cultures are said to encircle in historic buildings and are reflected in them. So a little example to start off with, and I've added a number of historical components to this about a lot of buildings as well. So put this in as an example of why our historic structures matter. So a little bit of history of the Leaning Tower of Pisa. I'm sure everyone is familiar with that building. It took 3 stages, and 177 years to build the Tower of Pisa. The architect Bonanno Pisano began its construction in 1173 with the first floor, which was surrounded by 15 columns of white marble and classic capitals. With the construction on the 3rd floor in 1178, the tower bent 5 centimeters to the southeast due to unstable subsoil, which the tower was built on, thus ceasing its construction. The period here when it was seized was very important because it allowed settlement of the ground. Otherwise, the tower most likely would have collapsed. 100 years later, Giovanni Simone resumed work trying to compensate for this inclination of the tower by vertically building 4 floors. However, the results were not as expected, and the bell tower still leaned, and work stopped again. In 1298, a plummet deviation of 1.43 meters was measured, and 60 years later, this figure had increased to 1.63 meters. Pisano continued the construction of the bell tower, whose works concluded in 1372. The inclination of the tower slowed down during the following centuries, and is believed that its weight was an important factor to allowing certain stabilization of the building. The architect Alessandro Gherardessa made the first restoration in 1838, eliminating the muddy soil and replacing it with a marble base. The result was not very good. This provoked a new tilt, and in 1918, the plumbing deviation reached 5.1 meters off the vertical. Until 1990, the tilt of the tower continued to increase to 1.2 millimeters annually. So in 1990, the tower closed its doors to the public as a security measure. Italian and foreign engineers planned to complete an 11-year, $27 million restoration project to reduce its tilt by 40 centimeters. It took longer, and in 2010, the restoration project was successful, which involved carefully extracting the soil from underneath the non-tilting foundation side of the tower. So I added this as an example because this, when I was in 1995, as I was a U of A undergrad, University of Alberta undergrad student, one of my professors, Dr. Rogowski, was a concrete specialist, actually worked on part of that restoration. So it sort of inspired me, and I knew I was in the right field, and we had a lot of discussions about what he was working on when he was looking at this, and it was really inspiring. So the prediction is that it'll take about 300 years for the tower to get back to its 1990 inclination. And added a quote that once Mark Twain said, is that the Leaning Tower of Pisa is the strangest structure the world has any knowledge of. So going to the Leaning Tower of Pisa, just wanted to add this slide in as well. A very different, we'll call leaning structure. So if you ever get a chance to visit Dawson City in the Yukon Territory, Northern Canada, you'll get a chance to see this unique and wacky, now tourist attraction. During the Gold Rush era, Dawson City was the largest city north of Seattle and west of Winnipeg. The Dawson Historical Complex that makes up much of downtown Dawson City is designated as a National Historic Site. It was the Yukon's capital from 1898 until 1953. There are 2 abandoned wood-framed buildings from the Gold Rush era in the downtown. On the right photo, you can see that's the restored area that's been is much of the downtown, but to the right you'll see the photos there. These 2 abandoned buildings are lovingly called the 2 kissing buildings because they fell in on each other due to changing conditions and melting permafrost foundations. Currently, this unique attraction is used as part of the Gold Rush era tour of downtown Dawson City to teach about permafrost and changing climate. So what makes it even more unique is that engineers and restoration specialists are currently working on methods to try to keep this building in a permanent kissing state. And again, I added this because many years ago, I did an initial assessment of these buildings to try to determine of some methods of how to stabilize it. Now, it makes it challenging, kind of, I guess, like the Leaning Tower of Pisa, because you want to keep it in that state. I don't know if we want to see the Leaning Tower of Pisa completely straight, or for these buildings if they stop kissing. So don't know if Mark Twain ever made it up there, but definitely I think he would add that to his list of strange buildings. So what is conservation? All conservation consists of actions taken to prevent decay. Within this objective, it includes a management of change and presentation of the object so that objects' messages are made comprehensible without distortion. Architectural and structural conservation is more complex. First, because a building must continue to stand up. Secondly, because economic factors usually dictate that it should remain in use. and thirdly, to resist the use and effects of climate. Lastly, thing to add is that there's a whole team of professionals that need to collaborate. So the doctrine of conservation was detailed and put forth by the International Council of Monuments and Sites, ICOMOS, in 4 charters. The Venice Charter, 1964, the Florence Charter, 1981, the Charter for Conservation of Historic Towns, 1987, and the International Charter for the Archaeological Heritage Management, 1990. And the first principles of these dated back to William Morris's 1877 Manifesto for the Society for the Protection of Ancient Buildings. So historical building conservation depends on a thorough study of the building as it stands, followed by any further analytical studies deemed necessary to make a correct diagnosis of the structural actions of the building and causes of decay. So in this way, it's rather like a comparison to medicine. The team consists of conservation architects, archaeologists, building economists, structural, mechanical, and electrical engineers, art historians, material scientists, and craft persons for each materials, as well as building contractors, surveyors, and town planners. Of course, the owners are also involved. So as in medicine, the needs of the patient must come first, and the architect should not hesitate to obtain a second opinion when necessary and should have the right to receive scientific support. All practical alternatives should be explored and then evaluated on the light of theory in order to find the least bad solution. So in that way, the conservation architect is, let's say, like the general practitioner, and then the engineers come in as maybe as the surgeons. Surgical engineer concentrates on stability and safety. And then we also have archaeologists concentrating on retention of original material, and art historians as well are included for specialist critics to train, observe, and interpret what is there. So it's a very big and involved team. So there's a certain standard of ethics that should be maintained by the professional team. First, number one, the regular inspections to determine the conditions of the buildings and structure should be recorded before any intervention starts. Its structural and material condition should be studied, and different phases of construction of the building complex, later interventions, and any internal or external peculiarities and the environment context of surroundings are all relevant matters to be included. Number two, materials and methods of restoration possibilities should be documented. Number three, historic evidence, the names and characters of the actual creators should be recorded, and no information should be destroyed, falsified, or removed. Number four, any intervention, restoration, or repair to prevent decay or deterioration. Minimal effect action is always the best. Allow maximum amount of material of the original to be maintained and least noticeable. And if possible, it should also be reversible or at least repeatable for the future. And finally, during restoration, aesthetic principles and concepts of composition and proportion relating to the building should be respected. Historical, physical integrity of the cultural property should be analyzed and understood in order to maintain the original concept. So how we should look at it, keeping the medicine analogy going, is that buildings are mortal. It should be stressed that there must be a point of time when a building will collapse if maintenance is neglected and that buildings are not repaired. So mortality applies in nature just as it does to the buildings we build. So mountains erode, valleys fill, and earth surfaces are altered by earthquakes and sea changes. The pyramids, for example, are structures that have immense intrinsic strength, but even they have lost a lot of their outer skin or gradually eroding due to the action of climate. So luckily, historic buildings are almost all over-designed and so have reserves of strength, but this over-design was not consistent. So some parts, therefore, are highly stressed and others cause strains or concentrations on weak parts to the point of collapse. So any study of the strength of a building must be 3 levels and considered first, the form of the whole structure, second, the structural elements, secondary elements like roofs and walls and foundations, and the soils that they sit on. And thirdly, the materials of which the components are made. So understanding history of unique materials. The first material to analyze and understand the strength, life of our historic buildings, a true understanding of historic materials, properties, and construction methods is essential. So the first material is masonry, and go to a little bit of history of the materials of masonry. So stone is one of the more lasting masonry building materials and has been used throughout the history of North American building construction. Stones most commonly used in historic buildings in North America are quarried stone, including sandstone, limestone, marble, granite, slate, basalt, and coral stone. The other type of stone is gathered stone, such as field stones, river rock, and boulders. These types of stones differ considerably in hardness and durability and other qualities. Building stones were usually laid with mortar, but sometimes they were laid without mortar using a dry stack method of construction. Brick is another masonry component, and that's it varies in size and in permanence. Before 1870, brick clays were pressed into molds and were often unevenly fired. The quality of historic brick depended on the type of clay available and the brick making technique. By the 1870s, with the perfection of an extrusion process, bricks became more uniform and durable. So brick also was then started to be used for architectural components. Architectural terracotta is also a kiln-fired clay product, popular from the late 19th century until the 1930s. It became more widespread with the development of steel frame structure, high-rise office buildings in the early 20th century. Also, there is glazed ceramic architectural sidings, which were used as cladding for high-rise buildings later on. And originally, adobe, which consists of sun-dried earthen bricks, was one of the earliest building materials used in the US, primarily in Southwest, where it's still popular. So after the materials, we'll talk a little bit about unique challenges in historic masonry maintenance and operations. So a few of the do's and don'ts of what we would want for these materials. So for example, for masonry, we do want to clean masonry only when necessary to halt deterioration or remove heavy soiling. We don't want to clean surfaces when they're not heavily soiled, where you create a like new appearance that needlessly introduces chemicals or moisture into historic materials. You do want to carry out masonry cleaning tests beforehand when determining if it's determined that cleaning is appropriate. So then looking at mortar and concrete. So mortar is used to bond together masonry units. Historic mortar was generally quite soft, consisting primarily of lime and sand with other additives. Portland cement, which came later on, creates a more rigid mortar, was first manufactured in the US in the early 1870s, but was not in common use throughout the country until the early 20th century. Thus, mortar used in buildings from around 1873 until the 30s ranged from traditional lime cement mix to a variety of sand and Portland cement combinations. After this time, most mortar mixes were based on Portland cement. Like historic mortar, early stucco was also heavily lime-based, increasing in hardness with the addition of Portland cement in the late 19th century. So then turning to concrete, it has a long history, is composed of sand, crushed stone, or gravel bound together with lime and natural hydraulic cements. As a construction material, concrete is used in a variety of forms, including blocks, block units poured, cast-in-place concrete, precast panels. So as well, cast stone was then and other manufactured products began to be used around the 1860s as substitutes for natural stone. In the 20th century, then things changed completely with reinforced concrete, and it was developed and has since become one of the most commonly used materials in modern building construction. So some of the unique challenges in historic mortar and concrete. For mortar, you do want to duplicate historic mortar joints in strength, composition, color, and texture when repointing is necessary. In some cases, a lime-based mortar may be considered when repointing Portland cement mortar because it's more flexible. You don't want to repoint masonry units with mortar of high strength Portland cement content unless it's the content was used in the historic mortar of the building. For concrete, you do want to investigate non-destructively to determine what kind, if any, reinforcing is in the concrete, conventionally reinforced, pre-stressed, or post-tension strands. You don't want to attempt to repair or cut any concrete without having an engineering study completed. This can be disastrous, especially for concrete with post-tensioned reinforcing. So looking at wood, wood is one of the most essential materials used in North America buildings of every period and style. Its many and varied attributes make it suitable for multiple uses, including structural members, siding, roofing, interior finishes, and decorative features. Many of the first structures in the early settlements were built with logs, which were readily available and did not require much finishing and could be quickly erected with basic tools. Water-powered sawmills cut logs into timbers and boards, but detailed ornamental features were generally still crafted on site using hand tools. Mechanized production increased the efficiency of cutting logs into timbers, boards, and more intricate components, and the structural and decorative potential of wood's use in building construction expanded. With more efficient production came lower costs, but also the standardization of ready-made moldings and assemblies for windows, doors, and decorative features. So the extensive use of wood in buildings can be attributed to its many properties that include strength in both tension and compression, the ease of which it can be cut and shaped, and capability to be connected using a variety of fasteners and adhesives. It can also be painted and varnished and has good resistance to wear and weather. Again, there was a change in wood industry, and engineered wood was starting to be developed. And one example I put in here was glue laminated timber, being first manufactured in the 1930s, is another engineered wood material, and it's important in that it's used for a lot of historical buildings because it's just its ability to span large distances. So it's used in a lot of mid-20th century buildings for massive arches and trusses in sports arenas and some similar large open column-free spaces. Oops, sorry. I just wanted to go through the challenges in historic wood maintenance. For wood, the do's are find and eliminate sources of moisture that may damage wood features, such as clogged gutters and downspouts, leaky roofs or moisture retaining soil touching wood around the foundation. You also want to apply natural preservatives or approved conservation chemical preservatives or paint to wood features that are subject to weathering, such as exposed end beams, outriggers, or rafter tails. And don't use chemical preservations such as creosote, which, unless used historically, can change the appearance of wood features forever. So steel. Wrought iron is a form in which iron was first used in North America in the beginning. Most wrought iron architectural elements were small, such as nails, ties, rods, straps, and hardware. Wrought iron features gradually increased in size to include balconies, railings, porches, steps, and fencing. It was not used for structural components until 1820, was the first time that cast iron columns were used. And cast iron building fonts and decorative structural and ornamental features followed soon after. Cast and wrought iron are often used on the interior of historic buildings as both structural and decorative features, such as columns, staircase, railings, and light fixtures. Metals commonly used in historic buildings include lead, tin, zinc, copper, bronze, brass, iron, steel, aluminum, and stainless steel. Historic metal building components were often designed by highly skilled artisans, and by the 19th century, many of these components were starting to be prefabricated and available in catalogs. Again, a change happened when steel, which is an alloy of iron and usually carbon, increased in popularity as manufacturing processes and production improved in the mid-19th century. Structural steel played an important role in the development of high-rise buildings and the skyscraper. So as a comparison of how steel advanced and changed, in 1891, the photo in the top left-hand corner, the tallest structure in the world was a 16-story Manhattan building in Chicago, which utilized cast iron columns with wrought iron beams. And that was 224 feet tall. Today, the tallest structure in the world is the Burj Khalifa in Dubai, utilizing steel design on a concrete base, coming in at slightly taller than 2,722 feet. So that is quite a difference and an advance in a short period of time. So unique challenges in historic steel maintenance are to clean metals when necessary to remove corrosion prior to repainting or applying other appropriate protective coatings. Do not fail to reapply coating systems after cleaning metals that require protection from corrosion. This can have a drastic effect and can start to corrode very quickly. And of course, as well, you do not want to take away the patina of historic metals. That keeps the historic fabric of the buildings. So now it's time for a poll question. So you'll see a poll question pop up if you can just, when you get a chance to answer. The first question, how many historic building structures do you have as part of your building and infrastructure portfolio? The second question, what unique building materials do you have to take into consideration when looking at planning and conservation of your building assets? And third question, what unique historic design features do you have to take into consideration when looking at planning and conservation of your building assets? So the results are coming back in, and they're still coming in. We've got a number. So just to quickly go through it, just to get an idea, just to share with everyone, what we're seeing is that pretty good, actually, over 27% have responded. They have over 27, well, sorry, that's gone up to 33%. And then, so about 2/3 go from, we've got 17% for 1 to 3, 17% to 5 to 10, and then over 20 is 33%. So pretty good background of lots of historic buildings in your portfolio. So challenges in operations and maintenance of historic structures. There are many unique challenges in the operations and maintenance of historic structures, but in order to extend the useful life as long as possible, we need to understand the causes of decays of the structural and architectural components. The climate is one of the fundamental causes of deterioration on buildings. So climatic causes of decay vary immensely the world over. The best techniques of conservation practice are required wherever climatic extremes are met, including possibilities if extreme events such as natural disasters occur. Traditionally, buildings have been built and designed according to specific geographical locations and built using local materials and methods which stand up best. So just a simple example is a mud brick or adobe hut can last thousands of years in extremely dry and desert conditions such as found in Nigeria, but less than a decade in the hot, humid climate of northern Peru. So adding to the challenges that over time climates are changing, weather patterns are changing, and simple protective building systems and traditional construction material types have a more difficult task. The resistance of building materials to climatic agents of decay decreases with exposure to these elements and with age. Even in temperate zones, solar radiation is found to be the more destructive, even more destructive than frost. Water in all its forms is the agent that promotes chemical actions and gradual deterioration of building materials and actively damages buildings when heavy rainfall overflows gutters and rivers rise during flood. So conservation and preventative maintenance efforts must be more involved in order to adapt. As our knowledge increases, our building codes are also adapted and changed. So one of the first biggest climactic effects is solar radiation. So solar radiation is the prime cause of climactic conditions affecting the Earth and its environment, cities, and buildings. Its intensity and changes have a direct effect on the Earth and its environment, cities, and buildings. Wavelengths for solar are measured from peak to peak range. Ultraviolet, 0.2 micrometers, narrow bandwidth visible light from 0.4 to 0.9 micrometers, and infrared 8 micrometers with greatest energy input. So different building materials vary in their ability to absorb different wavelengths, which equates to materials absorbing a certain percentage of energy. Light, especially ultraviolet component, is very destructive, particularly to organic materials such as wood, textiles, and pigments. And solar radiation causes fading, embrittlement in materials and loss of substance. For example, unprotected wood can erode at a rate of 5 to 6 millimeters or quarter-inch per century due to the combined attack of ultraviolet and rapid moisture exchanges. So a little bit on temperature and thermal expansion. The cause of air temperature change is almost entirely through the effect of the sun. There's a heating effect of the sun during the day due to short and long wave radiation. And then at nighttime, there's a loss of heat at night due to long wave radiation or convection at night. So building materials expand when heated and contract when cooled, and this thermal movement is a major cause of decay in buildings. In new masonry, movement joints are built into walls to accommodate thermal movement, brick expansion, and concrete masonry shrinkage. Expansion and control joints are required for nearly all new masonry construction, as well as concrete, but are rarely seen in older buildings. In historic construction, it's the softer lime-based mortars that allowed for more movement than contemporary cement-based mortars, like we touched on earlier. And movements are accommodated within the wall because of that now. So when considering adding expansion or control joints to an existing building, keep in mind that doing so may affect the overall performance of the given masonry wall and will drastically affect the visual reading of how the building is displayed architecturally. It cannot be overemphasized. It is critically important to inspect, maintain, and repair expansion joints and mortar on our main structural building systems and architectural wall and roof systems. So the action of moisture, the presence of water in various forms accelerates decay of most historic building materials. Corrosion is a significant threat to historic steel structures, particularly when moisture is present. Moisture in the form of rain, condensation, or humidity combined with oxygen leads to the oxidation of steel, resulting in rust and structural weakening. The presence of chlorides, especially in coastal environments, can accelerate the corrosion process. Faulty disposal of rainwater is the most frequent cause of deterioration in ancient masonry. Water can also penetrate through porous masonry materials, especially at foundations through capillary suction action. For old, thick masonry, this can sometimes show capillary rises as high as 8 to 10 meters. Another effect is through condensation. So condensation of water can be far more dangerous to historic materials than rainwater. This occurs when air is damp and the building surface, masonry or stone, are colder than the dew point of the air of water. It can sweep a large volume of air in front of the cold surface of the buildings and takes all of the dirt and gaseous pollutants, sometimes even sulfuric acid, and it forms on the masonry surfaces. Those particles of black carbon, iron oxides, and calcium sulfate and other substances are deposited and accelerates the decay of historic buildings. So frost and snow, it is not necessarily the extreme cold that causes damages to structures, that is the process of freezing. The resultant expansion of ice and the consequences of eventually thawing are the most damaging. Freezing damages porous structural materials such as concrete, brick, and stone, particularly if they're saturated with water. The resistance of these materials depends upon the size of the pores and their hydrophilic or hydrophobic structure. If ice forms in the pores of a material with adequate physical makeup in relation to the amount of moisture it will see, it can expand when freezing without damage. However, in prolonged frost with higher humidities, it may actually continue to build up inside the material because of condensation of water vapor and can be very damaging to structural elements. So the photos on the left are an example of a historic post-tension ferry and bridge at Trent University in Ontario. So this was one that we had assessed. It was a project that we had done. It's built in 1968 by famous architect Ron Thom, and beautiful campus. If anyone knows that area, it's quite a famous historic structure. We did a lot of assessments on that, completed a lot of non-destructive testing and material sampling, and some minor destructive investigations were completed. You can see that top photo there, the arch, the concrete in the arch, how the pattern on it, that it is, it has seen a lot of effects from freeze thaw. In the photo on the bottom, you can see when we were there was actually snow. So there's a lot of humidity from the river, and as well from rain coming from the top of it's a pedestrian bridge, and there was a lot of rain coming on the top of those arches as well. So there was a lot of humidity from both sides. So that's what you're seeing there is a freeze thaw effect on that concrete arch. So right now, a team is working on that to rehabilitate it because it needs some help. In northern climates, just to emphasize and talk a little bit about is the damaging effects of foundations. The design and construction method is to ensure that they're well built below frost level. In the far north, where the ground stays frozen permanently at certain depths, the challenge is to keep the foundations in those permafrost levels. If you remember the kissing buildings, otherwise there can be a lot of disastrous effects on foundations. So wind is the result of different atmospheric pressures in the weather system. Direction, speed, gusts, and frequency of calm periods during storms are all important characteristics of wind loading. So wind significantly impacts historic structures, causing two main damaging effects: direct damage and accelerating deterioration through moisture and erosion. So the first effect, direct, is such as direct roof damage occurs on architectural roof and wall coverings, such as stone tiles and copper, can be lifted by leeward side wind suction. Special design considerations are needed for connections, especially on improperly anchored roofs. Due to the effect and cyclical wind loading effects on roof elements, continuous investigation and repairs are essential. These can sometimes be simple remediation repairs, such as extra nailing, but that can also be very expensive and laborious. As well, another direct issue to look at for wind or concern is direct structural damage occurring for unique tall structures that are historically built, such as church towers, and can be very, very vulnerable to high wind pressures, leading to collapses or significant damage. Example that I put in the top corner there is the Norwich Cathedral in England, which is a tall 15th century church spire, 318 feet tall, the second tallest in England. Historically, it toppled once and was repaired and then had to be stabilized with steel rod ties due to the effect of the turbulent wind flow and the height of that spire. So, but it has, with that remediation and repairs, lasted 500 plus years. Although, just on a side note, while I was creating this the webinar and doing research, adding this as wanted to use this as an example of wind flows. There was a lot of information that came up in the last year that the cathedral is on the risk critical heritage restoration list of England. So it's actually been flagged because it needs some serious repairs, and it's very critical. And oddly enough, I was using that for wind, and it's not related to wind at all. It's related to the majority of repairs are needed are the damage and replace poor roofing and eaves troughs. So talking about how important water protection is to your structures. So the second discussion is for wind is accelerated deterioration, and that's just a wind-driven rain can push in water into cracks and pores in building materials and envelope systems, which accelerates their degradation. So wind pressure effects also creates erosion in combination with rain, which can cause serious surface deterioration, especially to weaker, more porous materials, as well as internal building material decay after it reaches its saturation point. This leads to a loss of material and structural integrity. And just wanted to highlight 8 of the 10 costliest natural catastrophes in US history have been wind related. Typically multi-billion-dollar wind disasters occur each year. So with that, a lot of building codes are changing and upgrading, especially when you talk about historic structures where you extend what you would design for. So for historic buildings, you can even for expected design life of 200 years is not excessive when considering wind design. So seismic activity. So we touch a little bit on just looking at seismic as far as natural disaster, because it's one of the most prominent ones. So earthquakes are different from other disasters in their capacity to destroy almost instantaneously and without warning, causing extensive, often irreparable damage to cultural property. So preparing for that and responding to earthquakes is key, and that involves local, provincial, state, and national or federal organizations. Improvements of the seismic resistance of historic buildings includes retrofitting if needed, based on updated design codes and data from seismic maps detailing most threatened sites. It should be integrated into a regular maintenance program based on periodic inspections by specially trained engineers. So time for another poll question. Should be popping up. Yep, there it is. Have you evaluated, so this, yes, so have you evaluated the climatic risks to your historic assets? And then the second question is a web-based where you can enter it in, but based on your geographical location and your knowledge, what are the top 2 climatic threats to your historic infrastructure? And then third question, what planning, remediation, conservation, if any, have you undertaken for your historic infrastructure? So they're coming in the responses just to share with everyone. We have you evaluated climatic risks to your historic assets? We have 83%, 86% saying no. And it's going up, 88%. Based on your geographical location and your knowledge, what are the top 2 climatic threats? It summarizes it just like a little bit, and it looks like the top one coming up is wind. Coastal locations are other ones that are coming up, tornado and other wind. And we have wildfire is another good one. We didn't go into a lot of different disasters and preparing for those, but there's obviously a lot of different disasters that have to be considered for historic buildings. Wind and salt. So definitely salt is another one that's coastal related. And finally, what planning, remediation, conservation, if any, have you undertaken to your historic structure? And the top one is none. So hopefully that will slowly change, and as well, hopefully you don't need to, because you don't need to do any, because they're all in good shape. So, and then we have remediation. We do have a number of risk mitigation, maintenance decisions, as well as FCI and time. Okay, so historic assets, planning for the future. So the first stage for planning for your historic building assets are completing condition assessments as safe record data management. This consists of preliminary visual assessments and study of each building. It's necessary to define as a whole historic structure. Should be assessed at regular intervals to establish maintenance plans and larger restoration and conservation efforts. An inventory and diligent search of records and archives should be undertaken for all historic structures in your portfolio. It is key that all documentation is maintained in a safe and accessible location. Does that sound familiar? It should be, because it's very similar. These are all part of plans for maintenance plans, but it's very familiar to the 3 mandates of ethical conservation. The condition of the building must be fully recorded before any intervention is begun. The materials and methods used during the treatment must be documented. And then finally, historic evidence must not be destroyed, falsified, or removed. So the 3 essential planning, pre-repairs, and remediation stages for historic sites are: number 1, the material, age, type, and uniqueness should be identified, retained in an original form, and preserved according to the documented historical material, and confirmed by conservation architects and the professional team. Number 2, deteriorated or damaged main structural and secondary structural elements should be stabilized until confirmed for safety or analyzed by a professional engineer. And number 3, maintain the useful life of historic structures using approved cleaning methods, preservatives, and protecting with envelope systems against the effects of life-damaging climatic threats and climatic events. Knowledgeable and experienced technicians and preservation trade experts should be part of that process. And definitely don't say deferred maintenance of your historic structures, please. So, as part of planning, modern tools and technology is essential to help understand and extend the useful life of your historic structures. To help maintain the original fabric of the structure with absolute minimal or no interference at all, non-destructive investigations are historic structures' best friends. So some of the key non-destructive testing methods that can be used: ultrasonic testing. High-frequency sound waves are transmitted into the structure, and reflections are analyzed. That's used to detect internal cracks, voids, and material thickness. Rebound hammer tests, Schmidt hammer tests, measure the surface hardness by analyzing the rebound of spring-loaded hammer. Estimates compressive strength of concrete or other materials. Ground penetration radar, GPR, uses electromagnetic waves to detect subsurface anomalies, locates rebars, voids, and moisture intrusion. Radiographic testing uses X-rays or gamma rays to create an image of internal features, detects cracks, porosity, and inclusions. And infrared thermography captures thermal images to detect temperature variations, identifies moisture intrusion, delaminations, and insulation defects. So this is by no means exhaustive, but there's a lot of different non-destructive testing that can be done. So specialized preservation, the future. Digital twin of the famous St. Peter's Basilica at Vatican City was created through AI, creating an ultra-precise 3D computer model that stimulates an object in the physical world. Called La Basilica de San Pietro, it involved drones, cameras, and lasers being used to take more than 400,000 detailed images to create an exact digital replica of the exterior and interior over a period of 3 weeks. Analysis then identified cracks and fissures invisible to the human eye that will help with restoration work. The results showed structural vulnerabilities. Surprisingly, there was a lot more extensive damage than previously thought. This project was developed by Microsoft and the Vatican in collaboration with Iconem, a French startup specializing in digital preservation of endangered cultural heritage sites. It's called, it was called one of the, or is called one of the most technologically advanced and sophisticated projects in assessment and conservation that has ever been pursued. So that's what the future looks like. It also revealed previously hidden or lost mosaic tiles and uncovered ornate ceiling, so archaeological events. So it's that's definitely what we have to look forward to for the future for historic structures. So to end with, we just wanted to end with a quick little case study for specialized preservation and early rehabilitation. And this was another project that we worked on as an assessment quite recently. So I wanted to, it's an interesting history, so I wanted to share a little bit about it. And it's the Canadian Natural Museum in Ottawa, Canada. So originally constructed between 1905 and 1911. At the time, it was named the Victoria Memorial Museum. It coincided with the pre-World War I boom in building encyclopedic museums, which most major cities were doing in Europe and North America. Architecturally, it was built as a large Tudor Gothic style, inside and out. Original materials were Tyndall stone and steel. And its building is located in downtown Ottawa, and it's very visible from Parliament Hill. Sits on a large park area. And in the original building, it had a towered entrance, and a photo on the left that is in the center of its highly symmetrical design. And it was a focal point of part of that original design. But due to unstable soil conditions, however, sounds familiar, the tower was substantially reduced in height 5 years after the building reopened. That's the photo on the right-hand side, shows that. So a little bit of the history then. It was continued on as the home of Parliament of Canada from 1916 to 1920 after fire destroyed the center block of Parliament buildings. It was designated a Natural Historic Site in 1990 because of its prominent and early place in the development of museology in Canada and because of its architecture. So included in that, when you're looking at preservation, is also when rehabilitation is involved and needed, and that was what was done with the museum. In 2004, 2005, it underwent a large-scale rehabilitation, which added a new glass front entrance tower to its facade, which is a modern throwback to the original tower. The main reason was for other restorations, but this was included as part of that restoration. It, as part of the major restoration, was undertaking major interior modifications to the museum display areas, including structural seismic upgrades. So this is considerations for seismic protection were reviewed and analyzed. And even though it's not considered a high seismic zone, such as on the West Coast zones of North America, it was still included in to protect the historic value of the building. So it's very unique because due to the benefit of modern lightweight materials, the original tower was reimagined and created and blended with modern architectural styles with the old. So just to end off with a slide, and I guess you've made it as a historic structure or building when you're immortalized in Lego. And just want to add, this is touring around right now, and there's a Lego build that was done of the museum. It took over 1,000 hours to create by a team. And it was designed over 2 years. And right now the model features over 100,000 pieces and takes 30 hours to set up. Includes all of the pieces to it, including that glass front entrance. I don't know if they got the seismic in there, but it's quite interesting to see. So just references for the webinar, a number of references if you're interested. There's a lot of good references there to conservation of historic buildings, standards and guidelines for the conservation of historic places in Canada, and the Secretary of the Interior standards for the treatment of historic properties from the US. Just want to end there and say if there's any questions, and then also have our links to our website, LinkedIn page, structural email you can contact me at as well. Just want to add, please stay after for a small survey after for the webinar. So thank you very much, and can open it up to questions if anyone has any.
Andre, it looks like a question has come up and it says, thank you. Can I have a copy of the presentation? And yes, we are going to be emailing you all with a link to the webinar presentation as well as a link to the slide deck. See, someone is typing a question in there. Oh, great presentation.
Thank you.
Yes, and
go
if you
ahead.
think of a question later, you can reach out to Andre at the structural@rothiams.com email. And as I said, you'll see that information in the deck. So I think that's it. Then, Andre, I think we can wrap up this webinar.
Okay.
Thank you, everyone who attended, and please stay tuned for more of the Roth IAMS webinars coming to you every 2 weeks.
Thank you very much.